It's important to properly dispose of unwanted medication or sharps. MedProject offers free and convenient disposal options near you. To learn more, call 844-MED-PROJECT or visit medproject.org.
Celebrate Thanksgiving with Safeway. This week at Safeway, get whole Signature Farms frozen turkey 10 to 15.5 pounds for $8 each, or 16.1 to 22 pounds for $10 each. Member price with a minimum $50 purchase, limit one per household. Plus, packs of Coca-Cola, Pepsi, 7-Up, Dr. Pepper, or AHA Sparkling Water are buy two, get three free. Limit 3 free items. Also this week, get 5-pound bags of Signature Farms russet potatoes for 97 cents each with digital coupon. Limit 1. Visit Safeway.com or head in store for more details.
This is SpaceTime, Series 25, Episode 26, for broadcast on the 2nd of March 2022. Coming up on SpaceTime, the Earth escapes a major geomagnetic storm event. Astronomers calculate the original mass of a dwarf galaxy shredded by the Milky Way. And NASA's Swift satellite captures the first ultraviolet light from a neutron star collision. All that and more coming up on SpaceTime.
Welcome to Space Time with Stuart Gary.
Planet Earth has escaped a major geomagnetic storm event. Luckily, the huge blast occurred on the opposite side of the Sun to the Earth, but had it occurred 15 days earlier or later, Earth would have been slammed by a significant solar storm. Scientists are describing the event, which was captured by both the Solar Orbiter spacecraft and the Solar and Heliospheric Observatory spacecraft SOHO, as the largest solar prominence eruption ever observed in a single image together with a full solar disk. Solar prominences are large structures of tangled magnetic field lines that keep dense concentrations of solar plasma suspended above the Sun's surface, sometimes taking the form of arching loops many times larger than the Earth. They're often associated with coronal mass ejections or CMEs, which, if directed towards the Earth, can wreak havoc on our technology and everyday lives. This event, on February the 15th, extended for millions of kilometers into space. The imagery was captured by the Full Sun Imager, which is part of the Extreme Ultraviolet Imager instrument on the Solar Orbiter. This instrument is designed to look at the full solar disk, even during close passages of the Sun, such as during the upcoming perihelion passage later this month. At its closest approach on March 26, Solar Orbiter will pass within 0.3 times the Earth-Sun distance. During that encounter, the Sun will fill a much larger portion of the telescope's field of view. But right now, there's still a lot of viewing margin around the disk, enabling stunning detail to be captured out to about 3.5 million kilometers, equivalent to 5 times the radius of the Sun. Other space telescopes, such as the ESA-NASA SOHO spacecraft, frequently see solar activity like this. But they're either closer to the Sun or further away, and they use an occulter, which blocks out the glare of the Sun's disk in order to enable detailed imagery to be undertaken of the surrounding corona. So the prominence observed by Solar Orbiter is the largest ever event of its kind to be captured in a single field of view together with a solar disk. It opens up new possibilities to study exactly how these sorts of events connect with the solar disk. At the same time, SOHO can provide complementary views to even larger distances. Other Sun missions are also watching this event as it unfolded, including NASA's Parker Solar Probe. Next week, Solar Orbiter and the Parker Solar Probe will perform dedicated joint observations during Parker's perihelion passage. Even spacecraft not dedicated to solar science felt the blast of this event. The ESA-JAXA Bepi-Colombo mission, which is currently near Mercury, detected a massive increase in readings of electrons, protons, and heavy ions with its radiation monitor. And while this event didn't send a blast of deadly particles towards the Earth this time, it's nevertheless an important reminder of the unpredictable nature of the Sun and the urgency of understanding and monitoring its behavior. This is Space Time. Still to come. An ancient dwarf galaxy reconstructed, and Swift catches the first ultraviolet light from a neutron star collision. All that and more still to come on Space Time. Okay, let's take a break from our show for a word from our sponsor, NordVPN. In an uncertain world, it's more important than ever to be safe online. And a secure and reputable virtual private network like NordVPN is a key part of any internet security. With NordVPN, you and your family can browse the web safely, securely, and anonymously. NordVPN encrypts your confidential data while keeping your online activity safe from the prying eyes of strangers and Big Brother. And NordVPN removes all those tiresome geo-blocking problems so you can watch what you want when you want. And NordVPN has over 5,300 servers worldwide, as well as the game-changing Nord Linux protocol that lets you stay safe without slowing you down. And that's important. When speed and security are a top priority, I highly recommend NordVPN. And right now is a great time to give NordVPN a go, as we've got a special offer for SpaceTime listeners. Here's the deal. Grab your exclusive NordVPN offer by going to nordvpn.com/StuartGary or use the code StuartGary at the checkout to get a huge discount off your NordVPN 2-year plan, plus one additional month for free, plus a bonus gift. And of course, it all comes with Nord's 30-day risk-free money-back guarantee. So, what have you got to lose? Grab your exclusive NordVPN deal today by going to nordvpn.com/StuartGary or use the code StuartGary at the checkout to get a huge discount off your NordVPN 2-year plan, plus one additional month for free, plus a bonus gift. And remember, it's all completely risk-free with Nord's 30-day money-back guarantee. And of course, you'll be helping to support our show. And you'll find all those details in the show notes and on our website. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
Astrophysicists have for the first time calculated the mass and the size of a dwarf galaxy that was shredded in a collision with the Milky Way billions of years ago. The findings, reported in the Astrophysical Journal, looked at the Ophan-Chenab stellar stream. Reconstructing the original dwarf galaxy, whose stars today thread through the Milky Way in a tidal stream, will help scientists understand how galaxies like the Milky Way were formed in the first place, and it could aid in their search for dark matter in the galaxy as well. One of the study's authors, Professor Heidi Newberg from the Rensselaer Polytechnic Institute, says the findings are based on computer simulations which trace the stellar stream back for several billion years. This allowed the authors to see what the original dwarf galaxy would have looked like before it fell into the Milky Way. Billions of years ago, this dwarf galaxy and many others like it, which were orbiting near the Milky Way, were torn apart by the Milky Way's gravitational tidal forces, and slowly, piece by piece, they fell into the larger galaxy and became part of it. These tidal forces distorted and eventually ripped the dwarf galaxies apart, stretching their stars into tidal streams flung across the Milky Way. Now, these tidal mergers are fairly common. Newberg estimates that immigrant stars absorbed into the Milky Way make up most of the stars in the galactic halo, the roughly spherical cloud of stars that surrounds the spiral arms of the central disk. Critically, the position and velocities of the tidal stream stars carry information about the Milky Way's gravitational field. Reconstructing the dwarf galaxy combined data from star surveys, physics, and Newberg's Milky Way at Home distributed supercomputer, which harnesses some 1.5 petaflops, that's a measure of computer processing speed, of home computer power donated by volunteers. This large amount of processing power makes it possible to simulate the destruction of a large number of dwarf galaxies with different shapes and sizes, and then identify the model which best matches the tidal stream of the stars seen today. However, only about 1% of the dwarf galaxy's mass is estimated to be made up of ordinary matter-like stars. The rest is assumed to be a mysterious invisible substance known as dark matter. Although they can't see it, astronomers know dark matter exists because they can see its gravitational influence on normal matter. The existence of dark matter is needed to explain the discrepancy between the gravitational pull of the mass of matter that we can see and the far larger pull needed to account for the formation and movement of galaxies. In fact, the gravitational pull of dark matter is now estimated to make up as much as 85% of all the matter in the universe. Tidal streams of stars from dwarf galaxies that have fallen into the Milky Way could be used to determine where dark matter is located in our galaxy. That's because tidal stellar streams are the only stars in the galaxy for which it's possible to know their positions in the past. See, by looking at the current stream of stars along a tidal stream and knowing they all used to be in about the same place and moving at about the same speed, astronomers can figure out how much gravity has changed along the stream. And that would indicate where the dark matter is in the Milky Way. The research also found that the progenitor of this particular stellar stream had less mass than galaxies measured on the outskirts of the Milky Way today. Newberg says if the small mass is confirmed, it could change science's understanding of how small stellar systems form and then merge together to make larger galaxies like the Milky Way.
There was a dwarf galaxy that fell into the Milky Way billions of years ago, several billion years ago, and the tidal forces from the Milky Way ripped it apart, pulled the stars off of it. They got spread out in the sky into this big stream, and we have been able to reconstruct from that stream what the dwarf galaxy that fell into the Milky Way 3 billion years ago looked like. And this is part of a longer-term goal that we have of trying to figure out where dark matter is in the Milky Way galaxy, a dwarf galaxy, in this case the Sagittarius dwarf galaxy, that is in orbit around the Milky Way. And as the dwarf galaxy goes around, the Milky Way pulls harder on the part that's closer and less hard on the part that's away. And so it stretches the dwarf galaxy and pulls the stars off. And when the stars are pulled off of the dwarf galaxy, then they start orbiting the Milky Way. And some get pulled ahead and some get pulled behind. And you get this big stream of stars which can circle all the way around the Milky Way galaxy. There's this higher density region that is the stream from that Sagittarius dwarf galaxy. But there was another stream, the orphan stream, and that orphan stream was called the orphan stream because we've never been able to find a dwarf galaxy that has made it. And so we think that dwarf galaxy is completely disrupted and doesn't exist anymore, thus the name orphan stream. But another group in 2018 looked at data in another part of the sky. Our data was in the north and this data was in the south, and found the Chenab stream, which is very faint. And they didn't know at the time that they named that stream that it actually is the same stream of stars coming from the same dwarf galaxy as the orphan stream in the north. And so because it was named two different things, and it's got both names in the literature, we now call it the orphan Chenab stream, or OCS. So you have a dwarf galaxy, and we run a simulation of it going all around the Milky Way. And then at the end of the simulation, we compare it with the data until we get a perfect fit. But doing that many simulations and trying that many guesses for what a dwarf galaxy looks like takes a lot of computing power. And luckily, we have about 20,000 people at any given time all over the world who are donating their computer cycles, the ones that they're not using, to our computations. And that is what Milky Way at Home is. We have a server that's at Rensselaer Polytechnic Institute, and we send out over the internet a work unit which says this is a bunch of parameters I'd like you to try, and these people all over the world will crunch through the numbers and tell us how good a fit it is to the data that we're trying to fit. And then we keep sending out more work units until we get a really, really, really good fit to our data. And here is the result. We have plotted in galactic coordinates, X, Y, and Z, where stars from that dwarf galaxy are spread out and where dark matter from the dwarf galaxy has been spread out. Now, we're only able to compare with stars because we can't see the dark matter in the tidal stream, but the dwarf galaxy has both, and the simulation can tell us exactly where the dark matter is. And so this gives us an idea that the stars are in a fairly tight stream across the sky, but the dark matter is a much wider stream that goes much further out. And that's because the stars start out closer to the center of this dwarf galaxy. And our result says that it's been 3.6 billion years that this dwarf galaxy has been orbiting the Milky Way and disrupting. And the mass of the star part is about 3 times 10 to the 5th, or 300,000 times the mass of the sun. The scale radius of how the stars were distributed in the original dwarf galaxy is about 200 parsecs, and the distribution of the dark matter initially was almost 4 times as much. So the dark matter is a larger distribution with a smaller stellar distribution inside it. And those are all numbers that are pretty close to what we would have expected for a dwarf galaxy, an ultra-faint dwarf galaxy falling into our galaxy. The surprise for us was that the dark matter was less than we expected. The dark matter is about 2 times 10 to the 7th, or about 20 million times as much mass as our sun has. And the dwarf galaxies that we see in the Milky Way today, even the ultra-faint dwarf galaxies, have masses that are substantially higher than that have been measured. And so that might make you ask, does that mean that dwarf galaxies have masses that are smaller than we thought? Does it mean the mass measurements of ultra-faint galaxies that exist today are wrong? And if they are wrong, that's a problem, because particle physicists are using that dark matter mass to set constraints on dark matter from their indirect detection experiments, which target dwarf galaxies because they have so much dark matter in them. Or is it that dwarf galaxies that are not disrupted today are just fundamentally different from a dwarf galaxy that fell in and got disrupted 3 billion years ago? But we're soft pedaling this a little bit because this is the first time we've ever used this technique to determine the mass and radial profile of a dwarf galaxy progenitor, and there are a few things that we need to check. One of the main systematics that we're trying to check is the effect of the Large Magellanic Cloud, and we didn't include the gravity of the Large Magellanic Cloud when we did our calculations. Now, we think that probably isn't, we're hoping that's not a problem, because we mostly used the data from the stars that are in the northern part of the sky, which are not much affected by the Large Magellanic Cloud, which is coming on the south side of the Milky Way right now. But that is something that we need to check, and there are other things. There are always many things that can bring a measurement off of what you think you've been able to determine. In the long term, it's my hope that we will be running Milky Way on a whole bunch of dwarf galaxies at the same time. And we will not be fitting just the properties of the dwarf galaxies that fell in, but we'll also be fitting simultaneously the orbits that they fell in on, the times that they have fallen in, and the properties of the Milky Way galaxy itself. And there's some evidence that we will be able to fit all of these different things at the same time with a sufficient software development. And if we're able to do that, and we're able to determine the gravity of the Milky Way galaxy at all positions in the galaxy, because we've looked at streams in all different places, then we can determine from that where the dark matter is, because dark matter is thought to be 85% of all the mass in the Milky Way. And so if you figure out where the things are that are causing the gravity, you're pretty much figuring out where the dark matter is. And that knowledge will help us to maybe understand what dark matter is, because certain properties of dark matter, how it interacts with matter, how it interacts with itself, will determine how it gets distributed in a Milky Way-like galaxy. And so that will give us a chance to study dark matter in the only way we've actually been successful in studying dark matter, which is by looking at how it affects the things we can see, like stars.
That's Heidi Newberg from the Rensselaer Polytechnic Institute. And this is SpaceTime. Still to come, NASA's Swift catches the first ultraviolet light from a neutron star collision, and later in the science report, does your life really flash before your eyes as you die? All that and more still to come on SpaceTime. On October the 16th, 2017, the advanced LIGO and Virgo gravitational wave observatories announced the discovery of a new type of gravitational wave signal, one which appears to have been caused by the collision of two neutron stars. The event had taken place 2 months earlier on August the 17th and was accompanied by a short-duration gamma-ray burst. It was the first time astronomers have actually observed the long-hypothesized collision of neutron stars. It also allowed them to confirm this type of merger is associated with gamma-ray bursts. Gamma-ray bursts are the most powerful explosions in the universe since the Big Bang of creation 13.82 billion years ago. And they're amazingly common. A gamma-ray burst occurs on average about once per day somewhere in the universe. They're very brief but intense flashes of gamma radiation that can be seen literally billions of light years away across the universe. They were first detected by the United States military, looking for telltale gamma-ray signatures from Soviet Union nuclear weapons tests. And the generals were shocked to find that not only were these gamma-ray blasts occurring every day, but they were occurring in deep space, far beyond the moon and far beyond what they thought the Soviet Union's capabilities were. It was only when they started talking to astronomers that it became clear that these were cosmic events and not man-made nuclear tests. Gamma-ray bursts come from all directions in the sky, and they can last from just a few milliseconds to a few hundred seconds. When this particular gamma-ray burst occurred, astronomers around the world began searching for its location. They eventually tracked it down to a relatively nearby galaxy called NGC 4993. NASA's Earth-orbiting Swift Space Telescope was then quickly maneuvered in position to look at the object with its X-ray and ultraviolet eyes. Within seconds of detecting the burst, Swift relayed its location to astronomers around the world. And both ground and space-based telescopes were quickly slewed into position to observe the burst's afterglow. Yet, surprisingly, Swift saw no X-rays coming from this merger. And that was a shock because higher energy gamma rays were produced. But instead it did find a bright and very quickly fading flash of ultraviolet light. The findings, reported in the journal Science, suggest that this short-lived ultraviolet flash likely came from material blown away by the disk of debris that powered the gamma-ray burst. Still, the bright ultraviolet signal was unexpected and reveals unprecedented details about the aftermath of the collision. The rapid fading of the ultraviolet signal suggested the outflow was expanding with a velocity close to a tenth the speed of light. The discovery of this powerful wind was only possible using electromagnetic spectrum telescopes, which is why combining gravitational wave observatories with conventional telescopes in what's termed multi-messenger astronomy is so important. This report from NASA TV.
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma-ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma-ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's Swift satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes. Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.
This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. Well, now that millions of people around the world have had their AstraZeneca COVID-19 vaccine, 2 studies reported in the journal PLOS Medicine have given the most precise results yet on the true risk of a rare blood clotting event caused by the vaccination. In one study, researchers found that the increased risk of blood clots after vaccine with AstraZeneca was between 0.9 and 3 cases per million people. A risk they say was small when compared with the vaccine's effect in reducing COVID-19 harms. The second study found an increased risk of rare blood clots in the brain that was equivalent to 1 additional event for every 4 million people vaccinated. Almost 6 million people have now been killed by the COVID-19 coronavirus since it first escaped from Wuhan, China. The World Health Organization says the true death toll is likely to be at least double that amount, however, with some 450 million confirmed cases globally. Italian researchers have noticed a striking expansion in the population of 2 Antarctic flowering plants, which they say is the first evidence of climate change accelerating ecosystem shifts on the icy continent. The study, reported in the journal Current Biology, says sustained climate warming since the 1950s has allowed for the plants to expand despite a major cold pulse in 2012. The authors say that while the warming may benefit some native Antarctic plants, it'll also lead to increased risks for plant invaders, which could trigger irreversible biodiversity loss and changes to the fragile and unique ecosystem. A new study warns that technologies designed to repurpose carbon dioxide from the atmosphere and turn it into useful products such as the fuel methanol are unlikely to actually mitigate climate change. A report in the journal One Earth reviewed 74 carbon capture and reuse technologies, finding just 4 that were able to reach the Paris Agreement target of zero emissions by 2050. Instead, the authors found that most of these fuel-generating technologies wound up releasing more greenhouse gases when used. The review warns that these technologies could end up diverting attention away from more effective options, such as carbon capture and storage, or simply pushing for greener reductions in emissions for the first time. So, does your life really flash before your eyes during death? Well, a new study reported in the journal Frontiers of Aging Neuroscience found that as you die, your brainwaves show up the same way as they do during dreaming, recalling memories, or meditating. And your brain remains active and coordinated for some time, both during and even sometime after heart death. The authors were measuring the brainwaves of an 87-year-old man during epilepsy when he unfortunately had a heart attack and passed away. They were able to gather information in the 30 seconds prior to and after the patient's heart stopped beating. Researchers say the brainwaves they recorded were usually involved in high cognitive functions and could be a literal example of someone's life flashing before their eyes. Telstra and TPG have announced a network sharing deal that's set to boost cell phone coverage across regional Australia. The multi-billion-dollar game-changing 10-year deal, known as a multi-operator core network partnership, will allow both companies to share mobile assets and spectrum. With the details, we're joined by technology editor Alex Zaharov-Reutt from ITWire.com.
Yeah, Telstra and TPG Telecom, which is the new name for Vodafone, have signed a network sharing agreement for regional and rural Australia. Now, currently in many regional and rural areas, Telstra has the only network available, unless, of course, you have a satellite phone. And I know, for example, I've got a friend that lives 30 minutes out of Tamworth. On one of my Vodafone-powered phones, I was able to get to Tamworth on the main freeway going up from Sydney with Vodafone most of the way. But about 20 minutes out from my friend's place, the Vodafone signal dropped completely. And when I arrived at my friend's place, there was just no service. But on my Telstra-powered phone, I had a connection. And the only other provider that has the full Telstra network besides Telstra itself is Boost. But if you were on Optus or Vodafone, you would have had no connection. You would have had to have driven into town to get a connection. So both Telstra and TPG Telecom has signed a 10-year regional multi-operator core network commercial agreement. And this is obviously going to be great for Telstra's wholesale mobile revenues, but it also delivers TPG Telecom's group subscribers with 4G and 5G services within a defined coverage zone across regional and urban fringe areas. And the brands that are underneath TPG Telecom is Vodafone, iiNet, Labara, and Felix. And Felix is most interesting because Felix offers unlimited calls, texts, and 4G data for $35 Australian per month. And that 4G data is capped at speeds of 20 megabits, which is more than enough to watch HD streaming content and do Zoom calls and all the rest for an individual person. And this will mean that many more rural and regional areas that weren't served by Optus and Vodafone will now have service through Vodafone's brands. But there is a catch. Telstra is keeping 1 million square kilometres of its coverage to itself. So there will still be areas that require you to have a Telstra-only device. But certainly there'll be a vastly increased coverage for Vodafone. And TPG Telecom's current 4G coverage will go from around about 96% to 98.8%. And this will also allow Telstra to gain access to TPG Telecom's spectrum across 4G and 5G. The different telcos have all purchased different lots of spectrum for 4G and 5G, And for Telstra to be able to get access to some of that means that it can bond some of the 4G and 5G channels together to give even faster speeds and to just give coverage in areas where it didn't have coverage before. Both organisations are going to still maintain sort of separate 5G networks, and this will also allow TPG Telecom to shut down a number of its sites whilst giving Telstra access to 169 of TPG sites. So it's a 10-year deal. Vodafone or TPG Telecom can request 2 sets of 5-year extensions, but it just means that there's going to be more roaming. It's also going to be extra competition from Optus, who's not part of this deal.
Well, the good people at Optus be thinking about all this.
Well, they'll probably want to know how they can get on board with some sort of deal as well. I mean, Telstra has the biggest network, especially in rural and regional areas, but Optus, for example, claims that it's got faster 5G on average in some of the main capital cities.
That's Alex Zaharov-Reut from ITWire.com. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.